Yesterday we introduced the concept of electromagnetic radiation. We said that EMR is pure energy that travels in a wave-like form. When we say it travels in a wave-like form, it really consists of two different waves. What are those two different waves that EMR consists of? What's one of them? One of them is an electric field wave, right? A sinusoidal electric field wave. What's the other one? Magnetic field wave. Good. Those two waves, the electric field wave and the magnetic field waves, are going to be perpendicular to each other. So maybe we've got an X, Y, and a Z axis. One of those waves, we'll say the electric field wave is on the Y axis. The magnetic field wave could be on the Z axis. Could look something like this. Not exactly like that. Can't really draw it. You know what I'm talking about though, right? They're perpendicular to each other. If one's on the x-axis, one's on the y-axis, then it's going to travel along the z-axis. If one's on the y and one's on the one's on the y and one's on the z, then it's going to travel along the x-axis. If one's on the x and one's on the z, then it's going to travel along the y-axis. Two fields, electric and magnetic fields, that are perpendicular to each other, and they travel perpendicular to both of those field waves, right? X, Y, Z. One of them is always going to be the way that it travels. The other two are going to be the electric and the magnetic field waves. What causes electromagnetic radiation? In general, what's the cause of EMR? Good. Accelerating, not just necessarily electrons, but accelerating charged particles in general. Somebody in the last class said accelerating particles. No, it's not accelerating particles. Okay, a car is a particle. When a car accelerates, it doesn't generate electromagnetic radiation. When a charged particle accelerates, speeds up, slows down, that generates electromagnetic radiation. We talked about Hertz's experiment. Hertz's experiment, if you remember from yesterday, was the experiment that experimentally verified, or that showed, that supported Maxwell's theory of electromagnetism. It essentially consisted of a big potential difference. We caused that big potential difference by a step-up transformer. That's not really important to us. We just need to know that we have a big potential difference that causes electrons to jump across this gap. As they jump across this gap, then they must accelerate. Hertz reasoned that if Maxwell's theory is correct, that accelerating charged particles generate EMR, then this should generate EMR. He throws an antenna over here to see if, in fact, there is EMR generated there. This antenna consists of a wire. This wire, when exposed to electromagnetic radiation, will have a current produced in it. The reason for that is because you got a changing electric and a changing magnetic field that generates an electric current. The idea here is this. If we detect a current here, then there must have been a changing electric and a changing magnetic field. Therefore, that portion of Maxwell's theory must be correct. The only thing that could have caused it would be this accelerating charged particle. Therefore, that portion of Maxwell's theory must be correct as well. Accelerating charged particles generate EMR, and EMR consists of a changing electric and a changing magnetic field. The 7 types of EMR we know from the song that we heard the last couple of days: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. They go in this order in terms of increasing frequency. As frequency is getting bigger, they go from radio waves to gamma rays. As energy is getting bigger, they go from radio to gamma. As wavelength is getting bigger, they go from gamma to radio waves. High frequency means low wavelength. So when we rank them in terms of frequency, we go one way. When we rank them in terms of wavelength, we go the opposite way. How are radio waves and microwaves produced? We group those together because they're produced in real similar ways. How are they produced? In general, they're all produced by accelerating charges, right? But specifically, how are these two types produced? What's that word? What was that O word yesterday? Oscillating electric charges. Charged particles that are going back and forth, back and forth, back and forth. Oscillating electric charges mean electric charges that are going back and forth, back and forth. It's AC current. Infrared, visible light, and ultraviolet are all produced in similar ways. They're all produced by what? You got to go ahead. Yeah, electrons and atoms, but specifically electrons that are on higher levels falling down to a lower level. So electrons making transitions in the atom from a high level down to a low level. X-rays are produced by rapidly decelerating electrons that are going really, really fast, and then slowing down to a stop really, really quickly. You go to a dentist office and you get an X-ray, and you get an X-ray every 1 or 2 years at a dentist office. They have what's called an X-ray tube. That X-ray tube is what accelerates the electrons to a really, really high speed. They use a potential difference, a really big voltage, a really big potential difference. It accelerates the electrons to a really, really high speed, and then they smash those electrons into a target. They make them stop really, really quickly. When that happens, the kinetic energy of these electrons gets transformed into light energy, into photon energy, electromagnetic radiation in the form of an X-ray. X-rays have a higher penetrating power than do visible light. Otherwise, it's exactly the same thing. When you get an X-ray taken, it's photography. You take a picture, normally you use visible light. Visible light reflects off of your body, the outside of your body, so that's what you see in the picture. When you get an X-ray, you're taking a picture, but you're not using visible light, you're using these X-rays, these X-rays that have a higher penetrating power. So they go into your body, they reflect off of bones, and then they come back out and you get the picture of it. So now instead of getting the picture of the outside of your body, you're getting the picture of your bones instead. Gamma rays are produced by nuclear decay. And nuclear decay can consist of radioactivity, nuclear fusion, nuclear fission. Any nuclear process basically is part of nuclear decay. Any situation where we have matter, mass, converted to energy. When matter is converted to energy, that energy goes off in the form of a gamma ray photon. We also need to know the frequency, the wavelength, and the energy of each of these 7 types of EMR. There's a range for each of them. We have to know 21 different ranges of numbers. That's the bad news. The good news is we only have to actually memorize 3 of them. We can figure out the other 18. The frequency range of microwaves is about 10 to the 9 to 10 to the 12 hertz. The frequency range of X-rays is about 10 to the 17 to 10 to the 20 hertz. And the frequency range of visible light is 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. Now, if you're asked what type of EMR you have when you have a frequency of 6 times 10 to the 14 hertz, you know that's going to be visible light. If you get a frequency that's 10 to the 18 hertz, you know that's going to be X-rays. And if you get something that's 10 to the 11, you know that's going to be microwaves. But what if you're given a frequency that's, let's say, 10 to the 7 hertz? We haven't memorized what type of EMR 10 to the 7 hertz is. So how do we know? Well, if it's smaller than 10 to the 9, then it's got to be radio waves. If we're given a frequency that's 10 to the 23, then we know that it's going to be gamma rays. If we're given a frequency that's 8 times 10 to the 14, then we know it's ultraviolet. If it's 2 times 10 to the 13, then we know it's infrared. If we can memorize these 3 ranges of frequency, then we can determine what category any other frequency falls into by just kind of filling in the blanks. Now, we also have to be able to know the wavelength range for each of these types of EMR. There's 7 of those as well. But the good news is we don't have to memorize any wavelengths because we can calculate frequency from wavelength and then compare it to what we just did in the first one. Let's use the equation that we learned in Physics 20 that relates frequency and speed together. Frequency and wavelength and speed together. Call it the wave equation. Let's rearrange that to solve for frequency. We get V over lambda. Let's say that you're given a frequency, a wavelength of 6 times 10 to the 14, 6 times 10 to the negative 7 meters. A wavelength of 6 times 10 to the negative 7 meters. We want to find what type of EMR that is without memorizing 6 or 7 or whatever different ranges of wavelengths. Let's calculate that as a frequency. Let's say the speed, which is the speed of light 3 times 10 to the 8 meters per second, divided by the wavelength 6 times 10 to the negative 7 meters, gives me 5.0 times 10 to the 14 hertz. What type of EMR do I have? What type of EMR has a wavelength of 6 times 10 to the negative 7 meters? What type of EMR has a frequency of 5 times 10 to the 14 hertz? Look at the board. It's visible light. So we didn't need to know the wavelength range of visible light in order to know that this wavelength is visible light. We needed to know the frequency range. We can calculate the frequency from the wavelength and then just compare it against those 3 numbers in red that you see up on the board. Do a similar thing with energy. From the energy, we can calculate the frequency and compare it with the first row.